We'll just, you guys can ask questions as you need to. So stuff like this. Evaluate the limit using plus infinity or minus infinity as appropriate. Okay, so how would we do one like this? So look at that for a second and talk to me about your process. Yeah, you're going to try direct substitution. If I do that, I get what? 0 over 0. Okay, so what's that mean? Yeah. The leading coefficient thing? Okay, now let's make sure. Okay, so the suggestion came up, and you're going to see some like that, where you take the limit of the function equals the limit of the leading coefficient. Now, when does that apply, and what kind of limit? Limits at infinity, right? So this is a little different. What do we do here? If I have 0 over 0, remember, that means more work. There you go. So we're going to factor. This is going to be the cancellation technique, where we're going to factor the top, factor the bottom, and cancel factors. Okay, you already know what are the factors that have to cancel here, because we're going to get a power of x, aren't we? Because as x goes to 0, that's the factor that would equal 0, right? And so this is one where I would just factor. How would I factor the top? Yeah, factor it into x to the 5th times x plus 9, and then I just cancel the x to the 5ths. It's the cancellation technique, and then I can take the limit directly. Okay? Good? So that goes back a long ways ago. What about one like that? What do we do? I'll let you look at it for a second.
You take the inverse of the radical of the root, so the root plus 7.
By inverse, you mean?
That the minus 1 on the outside is plus.
We don't even
Oh,
know
so
that it's
the
going to come out to a 0 over 0.
Aha! What do we do first?
Plug it.
We try to evaluate directly. Yeah, so if we evaluate directly here, we get 15. So already you know you got a non-zero answer on the top. So you're going to be done no matter what, right? And on the bottom you would get, what's that going to be? Square root of 16, which is 4 minus 1, which is 3. You're done. The answer's 5, right? So you always try direct evaluation first, always, right? You're taking a limit. And then if it doesn't work, then you move on and you have to do some kind of algebra to resolve the indeterminacy. Okay, now that one, if I try it, I'm going to get 0 over 0. So what would I do here? Archer, you are onto something here. What do you do?
Take the radical, and instead of it being minus 11, it would be plus 11. So you take radical of 121 plus h, and then plus 11. And multiply it to the bottom.
Good. Okay, so remember what we called that. So it's the rationalizing technique, and we do it by multiplying top and bottom by the conjugate of the expression that has a radical that goes to 0, right? So we would multiply top and bottom by square root of 121 plus h plus 11. Okay, if I do that, what am I going to get on the top? You're going to get 121 plus h minus 121 over a big ugly thing, right? H times okay. What happens on the top? Yeah, okay, the 121s cancel horizontally. Those guys cancel horizontally. And then I can cancel the h's. Those are gone, so I can cancel the h's vertically, leaving a 1 on the top. And then I just evaluate directly, right? Okay. Okay. Yes. Right, and that's the best way to do it. You can, I mean, you could just simplify the top and the bottom, but it's much easier to clear fractions, right? Clear fractions, top and bottom. So we would multiply top and bottom by the LCD of all fractions on the top and the bottom. Or there's only There are no fractions in the denominator, only fractions in the numerator. The LCD would be 7x, wouldn't it? Everybody agree? Product of the denominators. Okay, so we're just going to multiply through then everything. Let's rewrite this. Okay, so what do I do on the top? Yeah, when I distribute to the first term, I'm just going to, x is canceled, and I just get 14, right? When I distribute to the second fraction, what cancels? 7s, and so I get, okay, what do I do on the bottom? What do I do? Nothing. Yeah, I do not want to distribute, right? That's the whole point, is we want to leave it factored. So I get 7, I just leave it as 7x minus x minus 7. Okay, what do I do on the top? Factor out, what should I factor out? Negative 2, exactly. If I factor out a negative 2, what's left behind? Yeah, good. And so now we get vertical cancellation, don't we? We get those guys cancel, and I can evaluate my limit. Okay? How we doing? Good? So far, so good? Okay, so there's kind of a review of that stuff, you know, the solving limits or evaluating limits analytically. Those are all the different kinds of problems. Well, actually, there's one more. What about that one? What's the limit that we use here? What's the special limit we refer to? There you go. Okay, so the limit of, I'm going to call it a theta, sine theta over theta, as theta approaches 0 equals 1. Exactly. Good. So we need to have the same theta on the top and the bottom. Well, there's my theta, because that's what's inside the sine function. So I just have to multiply the top and the bottom by 10 here. Okay, so we get 10 there, 10 there. And then this is equal to the limit of, what can I do with that 10 on the top? I could just pull it out front, couldn't I? Right? That's the easiest way to think about it. So I get 10 times the limit of sine 10x over 10x as what? Right? And as x approaches 0, so does 10x, right? And so this whole thing then approaches 1. Okay, and what's my answer? 10. Yeah. Okay. Okay, so they want, it says find the limit of the rational function as x approaches negative infinity or x approaches infinity. Got to try each one, okay? Well, this is easy. We can just look at this and tell the answer. What's it going to be? Yeah, how come? There you go. As x approaches plus or minus infinity, it equals 0. Because we have a rational function with a higher degree polynomial in the denominator. And that's just one of our rules, right? Okay. What about that one? Okay. So on this one, right, and the answer on this one is, it's automatic. It's 8 because our rule, if I'm approaching positive or negative infinity and I have a rational function with equal degree polynomials, we always just take the ratio of leading coefficients. Yeah, good. Okay, Brandy, this is one where your strategy works too, right? Because we know that the limit of a rational function, the limit of a polynomial as we approach the infinities is always the same as the limit of its leading term. So we could, if we wanted to, we could also just write this as the limit of the ratio of the leading terms, 8x cubed over x cubed. And then the x cubes cancel and we just get 8. Either way, okay? It works. Okay, what about one like that? This is where we definitely want to use Brandy's approach. Yes, right. And how do we get that? So the limit of that function equals the limit of what ratio? 8x to the 6th over 8x squared. And what happens? Well, that just reduces to the limit of x to the 4th, right? Okay, and what's the behavior of x to the 4th? It's like that, isn't it, right? And so as x approaches positive infinity, the function approaches positive infinity. As x approaches negative infinity, the function approaches positive infinity. Now, if we had done something like this, then, if we had an odd function, an odd power of x, then we would have had differing behavior at the, at the extremes, right? Okay, give me thumbs on that. Does that make sense? Okay, all right. Okay, what about this one? What's our thinking on this one? Right. So again, we're looking at, there's a polynomial inside the radical, right? And so the polynomial is dominated by its leading term. And so we just end up with the limit of this function equals the limit of the square root of x squared over x, right? And square root of x squared is absolute value. There you go, the limit of the absolute value of x over x. And so now what happens if we approach positive infinity? What's that answer going to be? It's going to be infinity. No, it's going to be 1, right? Because as x approaches positive infinity, is x positive or negative? Well, let me say it again. As x approaches positive infinity, is x positive valued or negative valued? Positive valued. And so the absolute value of a positive input just gives me that input, right, as the output. That makes sense? Remember that piecewise function? We know that the absolute value of x equals itself when x is positive, and the opposite of itself when x is negative, right? So then this would just equal x over x, which is 1. Okay? How about the limit of the absolute value of x over x as x approaches negative infinity? Yeah, that's going to be now. So now that if x is negative valued, its absolute value is the opposite of itself, right? So it's going to be negative x over x, which is negative 1. And we know that because when we look at a graph of that function, what's that look like? Yeah, that's the stair step, right? It's got one big stair step where it just looks like that, doesn't it? Right? Okay? How about this one? as x approaches the infinities, what's going to happen to that function in the numerator? Yeah, right, the cosine is limited, right? The value of cosine can only swing between -1 and 1. So it's tightly constrained, whereas x can get really big, or in the positive or negative direction. So the function on the top is completely dominated by that -5x to the 5th term as x gets really big, right? And so this ends up the limit of y equals the limit of -5x to the 5th over x to the 5th. The cosine x becomes insignificant. And that's equal to -5 as I approach either positive or negative infinity. Right? Okay. Okay, there's the function g of x, piecewise function. They want us to compute the following limits or state that they don't exist. So what about the limit as x approaches -2? What would I do? Right, because it's a piecewise function. Remember what, for the limit to exist, the one-sided limits have to exist and agree. Okay, so for part A, we would take the limit of g of x as x approaches -2 from the left. Which piece would I be on? First, second, or third? First, right, where x is less than or equal to -2, okay? So that would be that piece. So we get the limit of 0 as x approaches, who cares? 0, isn't it? Right? The limit of g of x as x approaches -2 from the right, well, that's in that part of the domain, isn't it? I'm approaching -2 from values bigger than -2. I'd be on that middle piece, wouldn't I? Because I'm getting close to -2, right? -2 point something. So I got to be in there. So I get the limit of square root 4 minus x squared as x approaches -2 from the right. Well, that's going to give me what? If I evaluate that directly. 0, yeah. So what's that tell us? Limit is 0, yeah. Okay, so that tells us that the limit of g of x as x approaches -2 is 0. Okay, and I would do the same thing for part B as we approach 2, right? I'd take a limit of the red piece as x approaches 2 from the left, take a limit of the right piece, or the bottom piece, that we'll call that one the green one, as x approaches 2 from the right, and see if they agree. Okay, make sense? Okay, give me 1 to 5 on that one. How are we doing? Do we want to finish that one? Okay, all right. Do you want to do that last one?
No, it's okay.
Are you sure?
Yeah.
I mean, we can. I'm happy to. Okay. Why don't we? I think we should. Why not? Okay, so as x approaches 2. So now as, let's try this one. So the limit of g of x as x approaches positive 2 from the left, which domain am I in? Red, blue, red, or green? Red, right? Everybody agree? Because that's the place where x, that's the domain that includes values of x that are less than 2. We're approaching 2 from the left from values that are less than 2. Okay, so then we would be taking the limit of square root of 4 minus x squared as x approaches 2, and that's just going to give me 0, right? Oh, go ahead. Yep. Okay, now last one. How about the limit of g of x as x approaches 2 from the right? Which domain am I in? What color? Green. They want values of x greater than 2, okay? So I'm taking the limit of 4x as x approaches 2 from the right. Well, what's that? 8. Aha. Well, what do you know? The limit from the left and the limit from the right at 2 do not agree. So does the limit exist as x approaches 2? No. E and E. Uh-oh, I think this thing's going to blow up. Okay, so this one, E and E. Okay, does that help? Okay, so again, you got to take the one-sided limits and see if they agree, if they exist and agree. Okay, what about this? Take a look at that one and kind of think about how we're going to approach this. Okay, so think about, talk to me about part A. Okay, right. As x approaches 4 from the right, the limit of negative 2 over x, the quantity x minus 4 to the 5th, becomes what if I try to evaluate directly? Well, negative 2 divided by a number slightly bigger than 4 minus 4 is what? 0 positive, right? So I'm going to get a 0 positive to the 5th. Well, what's 0 positive to the 5th? 0 positive or negative? Positive. What's that mean again? It's approaching 0, but it's not, it never gets to 0, right? It's still a very vanishingly small positive number. And so negative 2 over 0 plus is what result? Negative and infinity, right? Because I'm getting a 0 on the bottom and a non-zero number on the top. Okay, how about B? The limit of negative 2 over the quantity x minus 4 to the 5th as x approaches 4 from the left. Well, what's that going to give me if I evaluate directly? Negative 2 over 0 minus to the 5th. What's 0 minus to the 5th? 0 minus, yeah, because I get a negative number to an odd power is negative. So the outcome is then positive infinity. And so what can we say about part C? No, it's not 0. Good, okay, all I can say is it doesn't exist because they don't, it doesn't exist in any of these three cases, but in part A, it doesn't exist, but at least we can say it approaches negative infinity. We know something about it. Part B, it doesn't exist, but it approaches infinity, right? Part C, it's a two-sided limit and they don't agree, so I don't get to say anything, right? Because they don't have consistent behavior from the left and the right. So all I could say about C is dne. Okay? All right. Vertical, horizontal, or oblique asymptotes. Okay, thumbs up or down. Does it have horizontal asymptotes? Down, right? And how come? Top's bigger, higher degree polynomial than the bottom, so it can't. So we know it doesn't have horizontal. What about vertical? At -5, say it again. Yes, good. X equals -5 is a unique zero of the denominator, right? If I evaluate this function at -5, I get a number divided by 0, right? So X equals -5 is a vertical asymptote. Okay? Give me thumbs on that part. Does that make sense? Okay, again, unique zeros of the denominator always correspond to vertical asymptotes. So there's only one of those, right? Because there's only one zero of the denominator. Okay, what about an oblique asymptote? How am I going to get that? Divide. Yeah. So we need to simplify this. Now, what would be the easiest way to do this division? Synthetic, right? Because I have a linear factor in the denominator. So we'll use synthetic division. What goes on top? What goes out front? -5. Okay, good. So then, what do I get? -5, because I add them, right? You do the opposite of long division. You add with synthetic. And then 20. So not that I really care, but that's a, oh, whoops, 25. Yeah. Not that I really care, but that's, what, 19? So what's that mean then? What is this, how does this simplify? It becomes divided by okay, and then if I take the limit of that as x approaches infinity, so let's go down here. What happens to that last term? Goes to 0, right? Because the bottom is a bigger power of x than the top. And so what we're left with then is our slant asymptote or our oblique asymptote. So we get slant asymptote at y equals x minus 5. That's the line that would define the asymptotes at the tails of the function for large positive or negative x. Okay? Good? Questions? Okay, and what's the, remember what we see here is, how did we know right away that we were going to get oblique asymptotes? What about this gave it away? Good, because the degree of the polynomial in the numerator is exactly 1 greater than the degree of the polynomial in the denominator. That means that when I divide these out, I'm guaranteed to get a linear function plus some remainder, right?
When you get x minus 5, what is the x minus 5
From here. What does this mean in synthetic division? Remember, this is the remainder, which makes that the constant, which makes this the coefficient of x, which makes the next one the coefficient of x squared. Okay, does that make sense? Okay. You could use long division, but it's just a lot of extra work. Use synthetic division when you can. Okay? Okay, so this one, determine the value a for which this function is continuous, first of all. And then it says state the value of the limit of g of x as x approaches -1. So I kind of made this one up, so it really just, this one example addresses a couple, 2 or 3 different questions on the test 1 and test 2. We can do this one, all those other ones will make sense. So what am I going to do? What has to be true for this to be continuous? Okay, so yeah, the shortcut you may be seeing, if you've done some of these, you know, on the homeworks, you're probably thinking, okay, when I evaluate these at -1, I got to get the same thing on the top and the bottom. But what are you really doing? What you're really doing is you're making the limit exist by having the two one-sided limits agree, right? For this thing to be continuous at -1, that's the only place where it wouldn't be continuous, right? On the top, I've got a polynomial. On the bottom, I've got a polynomial. They're fine everywhere. The only place this might not be continuous would be at -1. Well, we get to choose the value of a to make it continuous. So the limit from the left has to equal the limit from the right. Okay, so let's take a look at that. The limit of g of x as x approaches -1 from the left, from values less than -1, is the limit of that top expression, x squared minus 7x, as x approaches -1 from the left. Well, what do I get if I evaluate that at -1? Yeah, everybody agree? 8? Okay, so that is the limit of g of x from the left. It's set, it's 8. The limit from the right if I evaluate it directly is what? How do you get a number? -a minus 5. Agreed? Yeah. If I evaluate this directly at -1, I get a times -1 cubed. Well, that's just -a minus 5. Okay, now what has to be true for that limit to exist? They have to equal each other, right? So these two have to be equal, so let's make that happen. -a minus 5 equals 8. What do I get? A equals negative 13? Oh, hold it. Did I do that right? Yeah. Right, because remember that's... Right. Okay, so then the answer of A is -13. That's the value that we have to choose for A. Well, what's the value of the limit? What is it? Yeah, it's 8, right? Right, the value of the limit, we set it so the limit would be 8, didn't we? Right, they have to be equal. We already knew it's going to be 8 because it's 8 from the right, so we need to make it 8 from the or it's 8 from the left, we need to make it 8 from the right also, which we did by choosing the correct value of A. Okay? So this is 8. What's the value of A? Negative 13. Okay? All right. Okay, well, it asks you, why is f not, so it tells you it's not continuous at 0. Why is it not continuous at 0? I mean, what really has to be happening here? There has to be a break in the function, doesn't there? Everybody see that? I mean, if I so then which one is it? What's going to be the answer? That's the only thing that could happen, because for values of x less than 0, it's just going to be determined by that polynomial. I'm going to plug in values of x into that polynomial. For values greater than 0, I've got this polynomial. The only place it might not work is at 0. It's telling us it doesn't. We could do the limits, but what we're going to find is I'm going to get the limit from the left is not going to equal the limit from the right. Limit from the right is 0, isn't it? Right? Limit from the left is what? You can already tell. As x approaches 0. 5. Yeah, because those terms would just go to 0 and I'd be left with a 5. So there's going to be a break in the function there, right? A gap in the function. So it's a jump discontinuity. A, B, C, or D? Gotta be C, right? The limit doesn't exist, okay? Right, the limit doesn't exist. The one-sided limits don't agree, so the limit doesn't exist. Okay, which of those statements would be true? Is f continuous from the left at 0, from the right at 0, or it's not continuous from either at 0? Yeah, it's from the right at 0, you say? From the left. And again, how come? Okay, good, because that's where the endpoint is included. Because that's an equal sign right there, it's got to be from the left, doesn't it? Okay. Because think what it means to be continuous from the left. To be continuous from the left means that the function, that the value of the limit from the left equals the value of the function at that point. Well, that's true, isn't it? The limit from the left is 5, and the value of the function at 0 is 5. So the limit from the left equals the value of the function at that point. That's not true from the right because the function's undefined from the right. Does that make sense? As we approach from the right, we're approaching a value 0, but the value of the function is 5. So it's not continuous from the right. It is continuous from the left. Graphically, what does that mean in terms of graphing the function? Okay, yeah, if I put my pen on the function at x equals 0, then I could continue to the left without picking my pen off the board. If I put my pen on the board at 0 and I want to move to the right to values greater than 0, I'd have to pick my pen off the board to get to that other section, that other piece of the function. So that can't be continuous. I took my pen off the board. Okay? What are the intervals of continuity then? Well, what's the only place it's not continuous? So here's how we'd write it. Like that. Oh, that's wrong. Oh, no, that's right. That's, okay, so, yeah, okay, I disagree with that. I disagree with that. I think 0 should not be included. Yeah, so I mean, that's, they say that's correct, but yeah, I'm not buying that. It's not continuous at 0. Okay, I would give you credit for either one of those, though. Whether you put a bracket or a parenthesis there, I'd give you credit on the test, either way. Okay? You can make an argument for both of those, but I disagree with that one. Okay? How are we doing here? How would I use technology to approximate this? Okay, you could make a table. You could make a table, or what's the other option? Okay, you could make a graph and drag it along the graph. That one's probably not quite as good because it's going to be hard to tell what the decimal, if it's because it's going to be a decimal outcome. So a table would be fine. Just get close from the left and from the right. You could also just probably do what here? I mean, yeah, with technology, you wouldn't even really have to make a table, would you? You could just evaluate this function by plugging in a value like 0.9999999 and get a decimal answer, right? Plug in a value like 1.000001, get an answer, and you're going to see that they're going to agree, aren't they? I mean, you could, right? Does that make sense? They're going to agree out to 2 decimal places, and so you just round your answer to 2 decimal places. Okay, make sense? Okay, you just have to put in a point that's close enough to 1 so that the limits from the left and the right agree to 2 decimal places, and then just round that. Okay, so we're out of here. I'll tell you what, let's do. Why don't we, I want to finish going through this tomorrow, and then we'll talk about that other problem, and you can have, there'll be a little time left over. You can use that to, move the test to Friday, how about? Okay? I'll give people another day to work on the practice test and stuff too. That's fine. I mean, when you get back then, yeah.